Yeah. This talk is like joint work by me and Leonardo de Moura, who created Lean and is working at Microsoft Research. So I'm not sure, like, who of you has seen the previous talk about Lean by Johannes, or maybe otherwise knows about Lean? Okay, sure, that's completely fine, because I'll start with a short description of Lean. So Lean is a dependently typed proof assistant, meaning that it's based on the Carey-Howard correspondence. And like the one big feature defining it from other provers is that the kernel is that its trusted kernel is quite small. Okay, if this doesn't tell you anything, it doesn't matter. That's just a description of Lean. The only thing we're interested today in is that Lean can also be used as a purely functional and eager programming language. So yeah, just two short code snippets. Incidentally, they're the same ones Johannes has shown before, I think. So in Lean, we have like algebraic data types, like in many other functional languages, using more general inductive data types. So we can say a list over any type alpha, is either the constructor nil or the constructor const that takes one element and a tail of a list and creates a new list. And after that, we can define some recursive function like, say, map, that maps each element of a list over function f. So we say by case distinction, and after having defined some nice notation, the empty list is mapped to the empty list, and the const constructor is mapped to a new const constructor with the mapped head element and recursively the mapped tail of the list. So just to give you an idea what Lean actually looks like. And so why is Lean a programming language if it tries to be a theorem prover first and foremost? To explain that in a bit more detail, I'll give you a brief history of Lean. So the first official version of Lean was released in 2015. It was already called Lean 2. There's a version Lean 0.1, but that was a very different system. So Lean 2 already was a nice and tidy theorem prover you could really use, and you could like input your proofs as terms, as programs, much like, say, in other provers like Acta. But it also had like already this fixed set of tactics that you could use for some automation in your proofs. And then Lean 3 came along and made it much more general by making Lean a meta-programming language, meaning that you could build programs that build other Lean programs, or in other words, you could build Lean tactics directly in Lean. And so users could build their own tactics, but like the primitive, the hardcore tactics, like a simplifier or something, were still implemented in Lean itself in C++. So we didn't need a very big or great backend at that time. We had a pretty simple interpreter, and that was pretty much enough for executing the small tactics user actually wrote. Well, of course, it didn't take long until users actually started writing big tactics, and maybe they weren't satisfied with the built-in simplifier anymore. They now wanted to write their own simplifier or customize the built-in simplifier more and more. And so in order not to get swarmed by all these customization requests by users, the only way we saw forward for Lean was to bring all these tools, like all the tactics, but also like the entire front end, the parser, so that users could build more syntax, bring that closer to the users by re-implementing them in Lean itself, so that users could directly access all the functions and also just copy them if they wanted to further modify them. Yeah, so this is the Lean 4 project. We implement Lean in Lean, at least big parts of it. And yeah, to do that, we really need to make Lean a general purpose language, something that is efficient enough that you can write a parser or a simplifier in it. And yeah, so this talk is about one part, how we want to make Lean 4 more efficient, and that's the new object model for Lean 4. So as a further overview, let's see where the backend is actually situated in Lean. So yeah, so this is for Lean 3. We have some front end up here, and with the last step, the elaborator, the only interesting thing is you need to know about the elaborator is that in the end it produces some typed term from the user input, and we can pass that to the kernel, which just type checks it for consistency, but also we can pass it to the compiler if if it's a definition, if the term represents a definition. Yeah, we don't compile lemmas, it doesn't really make much sense. Yeah, so that compiler produced some bytecode representation, which was passed to the interpreter, and then the interpreter again can be used by the elaborator, for example, to drive your tactics to execute them. And this whole loop is what drives the Lean 3 metaprogramming. So this overview won't change much in Lean 4. We just want to have more and more efficient backends. So the first one we will write is just some simple C++ code extraction so that we can generate actual native code from Lean code. But yeah, I mean, since I've been invited here to the LLVM social, I'm obliged to say that we're at least thinking about writing an LLVM backend. And I mean, sure, it should be able to do a much better job than the C++ backend, since so we could just use more specific LLVM properties from there. So let's look at the Lean 3 object model in more detail, so I can tell you everything that's wrong about it. No, so as I said, it was quite simple and it did its job for the time. So this model is completely uniform. Every Lean value is a pointer to some reference counted object on the heap. Well, almost. It's actually a tag pointer, so any small number like 31-bit, we just store inline in the pointer with a tagged bit. As a first optimization. But if it's an object, then it's quite simple. It can either be a constructor value from a constructor application, it can be a closure, it can be any arbitrary precision integer if it doesn't fit into 31-bit, or in more general, could be any C++ object derived from some special base class. But I'm sure you want to see some bytes, so here are some bytes. So every object in Lean 3 starts with a 4-byte reference counter, then 1 byte for this object kind, like is it a constructor, is it a closure, and so on. And let's just say this is a constructor object, which really is the most common case. Then we have 4 more bytes for the constructor index, like say 0 is nil, 1 is cons. 4 bytes for the number of fields or constructor parameters. And then we have the actual fields, just, like I said, it's all uniform, they all have like pointer size and are tagged pointers. Okay, so how did that work out? Well, it did work out quite well for a start. Like originally, this was really only intended for driving tactics, and tactics were not supposed to be parallel. So actually, it was all single-threaded, and that's great. We can just do. We don't need atomic operations to manage the reference count, which is quite expensive. So that was great. Well, then it turned out, actually we want to save some objects from the tactics and later present them to the user. And since the Lean server is highly parallelized, it means they have to move threads. Well, that was a problem. So yeah, we just hacked around it and said, okay, let's just deep copy this object graph and copy it over to the new thread. And it worked. I mean, these are small objects and we didn't do it very often. So yeah, that was completely fine for the time. But the more Lean we actually re-implement in Lean, the more we actually want to use good parallelization. So this will not scale the solution. Yeah, more specifically, for actual reference counting, we just use C++ smart pointers everywhere in the implementation. So even the interpreter just shuffles smart pointers around, which was really simple. You don't have to care about the actual reference counting. But it also means that you cannot optimize the reference counting in a better backend. So you may know perhaps from Swift, for example, they have explicit reference counting operations in their intermediate representation and can optimize them. Yeah, and finally, there are some core types in Lean, like names and expressions that are everywhere and that are much older than these new VM objects. So they are not actual Lean objects. They are just some C++ data types. So anytime you want to access them from Lean, we have to wrap them in this VM external class. And yeah, if you want to access a subterm of a Lean expression, then we have to unwrap the term and then rewrap the subterm. And that's, each wrapping is one allocation. So that is very suboptimal. So, now I'll talk about the Lean 4 object model, what has changed in there, and after that I'll explain or try to explain why we did the things like this. So the one fundamental difference is that the Lean 4 object model is now non-uniform, meaning that not every Lean value has the same size. And in the lowest intermediate representation, we actually now have some types. It's not completely untyped anymore. So specifically, we have the usual array of primitive types that are used unboxed. So an int 8 is actually 1 byte in size. And well, all the other objects still share a single type that's still a tag pointer to a VM object. So no change there compared to Lean 3. And yeah, they can still be like a constructor, closure, big end, but they also learned some new tricks, like now we support arrays of boxed or unboxed values natively, and also native implementation of funcs, meaning like closures that are memoized and not evaluated more than once. So looking at those bytes, we again have a byte for this object kind, and then one more byte for the memory kind, which I'll talk about in a minute. And yeah, for the constructor object, now we actually see some small optimizations there. The constructor index now is only 2 bytes, so you cannot have more than 2 to the 16 constructors in your data type. And yeah, we thought that should be enough for everyone. Yeah. Followed by 2 more bytes of boxed fields, which hopefully should also be enough. And then 2 more bytes of, just what is the number of unboxed bytes in total in this object. Yeah, and then this is followed by first all the boxed fields, which still have like pointer size, and then all the unboxed fields with variable size depending on their type. So this is still like a strictly ordered between boxed and unboxed fields. And one big advantage we get from this is that like runtime functions like say free, like deleting an object that have to walk over the object graph can still do so uniformly. Like they can just read like, oh, how many boxed fields do I have in this object, and then just iterate starting from here the number of fields, and then they have visited all the objects in one object. So this memory kind. The default memory kind is quite simple. It's called single-threaded, and yeah, when you allocate an object in Lean 4, it will start as a single-threaded object, so you get non-atomic reference counting, which is fast by default. So when you actually move an object to another thread, the threading primitive, so we assume you will use our threading primitives and not do some weird tricks via FFI, then you're on your own. Will upgrade the whole object graph you're passing to the other thread to be of the new multi-threaded memory kind. And then you automatically get atomic reference counting, and yeah, you're safe again. Right, so I propose that this is safe, and mostly this is safe because, remember, Lean is a purely functional language. Everything is immutable. So it's actually not possible that you can store a single-threaded object in a multi-threaded object graph and so could get aliasing from multiple threads to it, because all the objects are truly immutable. And yeah, other memory kinds, we do want to support stack allocations, which do not need any reference counting at all. And the same is true for these region objects, which I'll talk about later. So by this point, maybe you've wondered, so where is the reference count actually in this list? So since not all the objects actually have reference counts, we simply allocate them or store them in front of the object, like at least in front of the object pointer for those memory kinds that have a reference counter. That's just a slight optimization. Yeah, so another question that I could imagine at this point is, so you're using reference counting. How can you claim that you want to create fast code? Well, I'm not sure what you think about it, but depending on which people you ask, either they say, oh, garbage collection is the best and reference counting can never come close enough to it, or it's exactly the other way around. Well, so the number one feature why we don't want to implement a GC is because it's simply too hard and we have other things to do. Like, we're not first and foremost building a language. We're still building a theorem prover. And so actually, when you look at OCaml as one language that is quite close to Lean, since it's both functional and eager, and also has at least some pure data structures, you can find this multi-year, multi-core OCaml project that's trying to bring OCaml to, or bring multi-threading to OCaml. And yeah, on their website, they immediately state that the biggest challenge is implementing the garbage collector. So that's exactly the thing we want to avoid in Lean 4. Furthermore, it's simply easier to use a reference-counted object model from other languages, say from the C++ Lean part, but also any other language that wants to work with Lean objects. Basically you just have to build a smart pointer for Lean objects to store in. And yeah, another advantage is, again, everything is immutable in Lean and eager, so it's not actually possible to create cycles in the Lean object graph, meaning that reference counting is actually like complete. There are no cycles that will never be deallocated. And finally, there's one thing that garbage collection actually cannot do. It cannot tell you, oh yeah, you actually got a unique reference to that object, so instead of creating a new object, why don't you reuse that one when modifying it? Like, instead of a functional update, just do a destructive update to save allocations. So you may notice it's one thing that some implementations of linear types, or sometimes called uniqueness types, can provide. But yeah, we do the same thing, but just checked dynamically via the reference count. So there are multiple reasons for that. well, the first one is that we really think dependent types are hard enough, both for users and for implementers. So yeah, we really don't want to bother users with linear types, or ourselves. Yeah, and well, furthermore, it's of course true that dynamic analysis is always more precise, or can be more precise than static analysis. Yeah, could also be like less predictable if the user does not do annotations where they actually expect destructive updates to happen. But yeah, I mean, we'll see about that. Okay, so to give you one example of what this means, yeah, let's go back to our nice little map function, and let's think about what could we actually do here with linearity, with destructive updates. So yeah, we see, I mean, in the second case, we take one const cell and transform it into another const cell. And well, one important property is that if we have a generic type like list alpha in Lean, we assume that the alpha is always boxed. So all lists have the same layout, which really simplifies many things. So yeah, this means that these two const cells actually have the same layout. And so if this one is unique, like we're consuming it, we can just reuse it to build up this one. And it will be, yeah, we can actually make map allocation free. Yeah, so you could do this using linear types. Then you can map unique lists to new unique lists without allocations. But yeah, using dynamic analysis, you could actually say, like, as long as your list has a unique prefix, you can reuse that part, and only after it's being shared, you start allocating things. So that's where dynamic analysis is yeah, more precise than static analysis. Yeah, so let's look at the, well, not very nice code that Lean actually compiles for this. This example. So this is the low-level normal form, how we call it. And well, it may look still a bit like Lean. I don't know if it looks like that to you. So we are actually using the Lean term type, the same type in the whole compiler. And yeah, it really simplifies many things. But I mean, this code would not type check in the kernel. It's just in the compiler. It's an intermediate representation. Okay, let's try to read it. So this function takes two arguments. Yeah, the function f and the list axis, and then there's a case distinction on axis. So in the first case, well, we first decrement f because yeah, we haven't used it, so we should yeah, decrement it and perhaps free it if that was the last reference to f. And then we return a new object of constructor index 0, or in other words, the nil list. Okay, so here you may already wonder, okay, why are we not just reusing axis, which we know is an empty list? We could do that. In this case, it doesn't really matter because yeah, the nil list doesn't take any parameters, so we actually store it as a tag pointer. We do not actually allocate it. Yeah, and then we have the big second case, cons, where we start by projecting the two elements of axis and increment both of them, since we now have more references, one more reference to them. Yeah, then we use this reset instruction on axis, which means decrement axis, but if you reach reference count 0, do not deallocate it, because we may want to reuse it. But do decrement, in this case, it's two objects that are stored inside of axis so that their reference counts are still correct. Yeah, it's a bit of magic. Well, after that, we just apply the closure f to the head and do the recursive call with f and x4. And finally, we actually create the cons cell meaning constructor index 1. This reuse is almost like constructor, taking the new head and the new tail, but also as the first parameter, it takes an object we may be able to reuse. So if this object has reference count 0, this x5 from the reset instruction, then we do not allocate here, but just reuse the same object. And yeah, so with this we can actually get like 0 allocations in the map function if the input list is unique. Yeah. So I have to say most of the things in this talk are ideas that we can't benchmark yet because we simply don't have a backend yet to actually run this code. So I can't show you any numbers from actually running this function. Well, I can show you something that's almost as nice. Well, we already have implemented the actual object model in C++. So we simply wrote our own implementations of the map function in C++, like what we think the compiler in the end should produce for this function. And yeah, so then we can actually benchmark like a simple invocation, like we have a list of 4,000 natural numbers and just increment each element in the list. Okay, let's see. So if we just compile down the list to the map function, do no reuse, we get like 214 microseconds or something. And well, the important thing is we see that we immediately get like a almost 10 times speed up if we actually do this reset reuse optimization. So do linear updates, even checked dynamically. After that, there are just some possible optimizations. So, the optimized reuse means, well, I've said that this reset, if axis is unique, then it will decrement its two fields, which we've just incremented before. So, yeah, if at least in the C++ code we optimize that and remove the inc-dac combinations, then we actually get like another 50% speed up. And then just as a last version I checked, well, what happens if we actually assume the input is unique and remove all the branches, then we actually see that's not a big speed up. So the last line, that could be something a language with linear types could produce. But well, then you actually have to have two different versions of map and the user has to decide which one to call. So yeah, I think we're fine with the numbers above that. Okay, let's see. So one more trick you may know, I think, from Swift is sometimes we do not actually need these exact reference counts. So for example, if we have a function length that just returns the length of a list, we know we can't do destructive updates on that list because we're not generating a new list. So we can just, or we're at least planning to have like an attribute borrowed that says, okay, actually I was too lazy to increment this argument. So just assume it's shared. It's never unique, just assume it's always shared. And yeah, then we actually can like generate code for this function that does not have any reference counting operations. Yeah, so this borrowed attribute simply delays RC operations, which in some cases may mean that you can actually completely avoid them. But it does prevent linear updates. So yeah, in that case, you actually have to decide as a user what to do. Yeah?
Do you plan to infer this borrowed attribute by using static analysis, or does the user always have to specify it?
It seems like something you may be able to infer, at least in some
simple cases like
yeah, exactly. But yeah, I think for a start, it will probably be unique, be explicit, like applied by the user. Yeah, but yeah, it's something we could definitely do. Okay, and yeah, lastly, I want to talk about these regions and the issue they are trying to resolve, which is startup time. So in Lean 3, when you start up the Theorem prover, this doesn't actually scale very well because, well, first you have to deserialize all your dependencies from disk into memory, like the whole standard library of Lean. And yeah, I mean, this takes both time and memory to do. So it's just crazy. Well, it's the simple approach, and as far as I know, actually, basically all the dependency type provers do exactly this. For an alternative, actually, there's, for example, Isabel. I think there are some Isabel people here today. Okay, a few ones. Yeah. Okay. So I'm probably not telling you anything new. So in Isabel, you can actually take your dependencies and compile them basically into a single ML heap image that you can directly load into a new process. Just speeding up startup, like importing and all the processing you have to do with imports. So that's great. I mean, could be even better, I guess. Well, one slight disadvantage is you only have one heap. You can't load more than one into your process. If you want to do that, you have to just recompile your new set of dependencies. We still need to read the whole thing from disk first before we can do anything else. And I think they probably do some more patching on the loaded image. I'm not actually sure about that one. And lastly, I believe it's about as fragile as it sounds, like loading a heap into a process from disk. And so, for example, at least right now, you cannot actually create these heaps from inside an Isabel IDE session because there are simply too many other things in the heap that do not have anything to do with dependencies, and that you first have to very carefully deallocate before creating a heap image. So you always have to fall back to the command line to do that. Okay, so at some point I asked Leo, after shortly considering my sanity, what if we could just memory map regions of objects directly into memory without any transformations? I mean, if we could do that, that would be great, because I mean, it means we can do that multiple times, and actually, the operating system will do the lazy loading and the prefetching of pages for us, and I think it knows pretty well how to do that efficiently. And especially there are some parts in our imports, like proof objects, that we don't usually actually need to load. So if we could just maybe store them at the end of the file and then the operating system will never touch them, that would be really great. And then remember, everything is immutable in Lean. So these pages that are loaded, memory mapped into the Lean process, could actually share it by multiple Lean processes and do not have to stay in memory. So basically memory importing would actually be memory free in this case. We just have to be a little careful that our data is truly unique, so we should not touch reference counts in this data. And that's one reason why the region should not have a reference count. And then everything is truly immutable. Okay, so how could we do that? So this is not implemented yet either, but we're thinking of a non-crazy approach, perhaps, which is to say, we just store these objects with relative pointers, and then at runtime, we have to do a branch and see if it's a region object, then transform that pointer while you access it, else use it as an absolute pointer. So okay, there's one more branch, but I mean, we'd have to check how expensive that branch actually is. And then there's maybe the crazy approach, which is to say, well, we just try to memory map each region to its original address so that the absolute pointers are still correct. Okay, I mean, you can say, you can tell memory map to, okay, try to load it at this address, please, and it will try to do that. If it fails, well, I guess then we have to just go back to eager loading this import and do some pointer patching. But, well, 48-bit address space is about as empty as outer space. So I tried to do some quick birthday paradox calculation. So say, I'm not 100% sure this is correct, but say we have 100 dependencies we want to load into our process. Each of them is about 10 megabyte big. We're on a 64-bit machine, so we have at least 48 bits of address space available. And then, yeah, the probability of having at least a single collision between these 100 dependencies is about 0.018%, if I didn't make a mistake. Yeah, and just for clarity, in either of these approaches, writing the objects to disk is not free. This is just about loading them. For writing, we first have to actually collect them into like a contiguous region of objects. So that's like still hard and expensive. But fortunately, yeah, you usually don't write these objects nearly as much as you load them from disk. So that would be great to have. And yeah, for last point, for what we need to make this work is, well, if we want to use region objects for our data, it means that all this data must actually be lean objects, which is completely not the case in lean 3. Like I've already said, these core types were not lean objects in lean 3, but now that we have unboxed fields, it's actually feasible that we can re-implement, say, the expression type as a lean object. Okay, so I have some actual C++ code here. I apologize for that. But just to give you an idea of what the runtime actually, or using the runtime actually looks like in the lean C++ code. So to create a constant expression from, yeah, it's like the name of the constant and some universe levels, whatever that is. Yeah, you have to allocate a constructor object, give it some constructor index of the const expression kind, give it yeah, the 2 unboxed fields, and finally the size of the unboxed data. And then there is a separate call to actually set that unboxed data, which in the expression case is like the hash of the whole expression, and some flags like, oh, does it have a meta variable? Does it have a parameter somewhere in there? Yeah, so this is like just bookkeeping metadata that we use for optimizations. But the nice thing is that the lean type actually doesn't have to be this ugly. So the lean type actually just says like an expression has a const constructor that takes a name and a list of universes. And because all the other data is at the end of the object, we can just hide it from lean. So if the compiler actually tries to access any of these fields, it will still use the correct offset. Yeah, so we can simply hide all this crap from lean users, and they do not have to worry about it. Yeah, that's all the crazy features I have for today. To give you some idea of where we're actually at in the implementation. So I said we already have the model, the object model implemented in C++. We can actually write programs using it, just not lean programs yet. And yeah, these core types are also already ported to the model. So it's actually already being used heavily in lean, since, yeah, I mean, half the time of lean is probably spent on manipulating expressions. And yeah, we do have an optimizing compiler from the core Lean terms to this LLVM form, which does like inlining, but also specialization. That's new in Lean 4. Lean 3 could not do that. And yeah, just general simplifications of the intermediate representation. So actually, also using this joint point representation, this is very much inspired by the Glasgow Haskell compiler. So yeah, we're just stealing the best optimizations from them. And then we also have, since we still want to actually run some code already, we have a compiler from the new low-level normal form to the old bytecode format of the old interpreter. So we can run Lean 4 code that has been optimized using the Lean 4 compiler. It just won't use the actual new object model yet, because the old interpreter is still using the old object model. And what's still missing from this talk is an actual backend that uses this new model, and which also means that we have to re-implement all the build-ends using the new model. This whole writing and loading regions stuff has not been implemented yet. And further down is the actual multi-threading support, like the primitives and the object graph upgrading, and also this borrowing annotation is just an idea for now, as something that we may consider implementing in the future. Okay, so in conclusion, I've presented like a new object model that we've really tried to customize to what we need in a Theorem prover. And we can actually utilize some nice properties of this being an eager and purely functional language. And in the end, what we really want to do with it, with all the optimizations, is to avoid allocations wherever possible. Both during startup, when loading dependencies, and at runtime. All right. Thanks for your attention.
Very nice. Well, thanks a lot for the presentation. So we have an infinite amount of time for questions, but I think we should focus on a couple of core questions and then move some of the other stuff during like the more social part.
Yeah.
But if there are any immediate questions, I'm sure you might have some time to answer them. So.
I'm more on the user side. I'd really like to use Lean 4. How much effort is sort of left after you've implemented essentially what I've seen as the core runtime?
Right.
Is it going to be smooth writing then, because it's every Lean 3 library works on Lean 4, or?
That's the core question, of course, So let's see. The parser, we have a new parser for Lean 4, it works. So the frontend is slowly shaping up, and as soon as we can actually run code using the new backend, that's also nice. Then we have, I'd say, a good foundation. After that, there are still many little parts that are missing. Like we have to re-implement the whole tactic framework, because it will be, at least the low level will be different and be more efficient. And in general, there's no guarantee that your Lean 3 code will work in Lean 4, and most probably it will not without at least some like superficial changes. We still have some work to do, and I'd better not give you any time frame for actually finishing.
But it can't be like after 2019, because you had a one.
Yes, right. Actually, I only thought about that today, I think. I was like, oh, okay, well, then I guess it's like that, But so what I probably should also tell is that, so Lean is an open source project. Lean 4 is not open source yet. Like, it's just me and Leonardo de Moura working on it in private for now, so that we can have our piece from Lean free users. And yeah, but I mean, we do want to write some papers also about this topic, and so I mean at that point we will have some Lean code ready and published. So yeah, I mean that maybe will be like the next stage, and then I mean after that maybe we can start a beta and actually have people trying to start using Lean, and yeah, let's see from that. Yeah.
I was just wondering how much code you have to write to try to crash it.
To crash the runtime, or in what sense? Like
never finish, you know, like this.
Sorry.
Or maybe that will never finish solving.
Oh, you mean like a tactic that doesn't terminate? I mean, if it's your tactic, that's trivial. Yeah, I mean, so Lean, even in Lean free, it doesn't have any big solvers like built into Lean. Like the simplifier, I mean, can be slow, but it should always terminate. Well, not if you give it like non-terminating simplification lemmas. Okay. Okay, so it very much depends on your tactic. I think that's the answer. Yeah.
So in the end, you really want to be sure that when you've proved something, it's right? And
yes.
I guess, like at this stage, like there's a potential that if you get something wrong here, that will have consequences, so that you will eventually be able to prove something that's not actually true, right?
Yes. So the basic infrastructure is that anything you've ever proved will always go from the elaborator to the kernel, and the kernel will type check it completely in separation from the compiler. So even if you have a tactic, it has to produce some term that will eventually have to pass the kernel. So the compiler is not part of the trusted code base. At least until maybe we start doing, like there's this whole reflective proof parts that do some actual computation in proofs. Then it gets more complicated. If you want to like make that fast, then maybe you do want to have some computation engine in your kernel. But yeah, it probably still wouldn't be like the whole compiler. Okay, then.
All right. Yeah, I keep my question for later. Yeah, so let's thank our speaker again.